Bismillah ar-Rahman ar-Rahim. Assalamu alaikum, dear students. Welcome back in lecture 9. Student, basically we start this major assignment from lecture number 1, and now we are at the end of this assignment. Okay, we do all these questions, and we start this question number 6 in lecture number 8, and in lecture number 8 we didn't complete this question, so that's why this, inshallah, in this lecture number 9 I will cover it. Okay, so let us come back to the question. And basically one thing I want to show you, that in question number 5, basically it is very important to note down what is basically this y2, right? You see this one here, because it will help us in upcoming part of the question number 6, basically, which is remaining. You see that y2 is nothing, it is the distance from the top flange of the web, basically, to the neutral, to the center, you can say, to the compression force, or to the compression of the concrete block. Okay, so this is basically y2, but you should remember this y2 is basically counted from the plastic neutral axis location. Okay, in this case basically we are assuming that the plastic neutral axis, basically it lies at the top of the flange. Okay, so make sure that this y2 is basically covered from, is measured from the new plastic neutral axis. I think so. Please confirm it. Okay, now this y is basically the lever arm. As we are covering question number 6, and question number 6 is basically a part of question number 5, therefore you should keep this data in your mind. We have determined the c, and the c is basically nothing. It is, remember also that this is summation of q in, basically, and it comes out to be this value. Okay, and this value will help us in our upcoming question. Okay, here we have determined the value of a, and this value is 1.8. It will also be used here. We use y2 is nothing, it is the concrete thickness minus a over 2 times a over 2, and this y2 is basically comes out to be, I think so, 5 minus a over 2. I didn't write it, but you must make sure that what is the value of y2. Clear? This is lever arm. Okay, and this is 13.1. so we start question number 6. Basically we cover all this portion. Clear? We check it for the compactness of the section, then we check it for the flexure before covering, flexure after covering. We check it for the shear before covering and after covering. Clear? Here you see after covering, flexure, and shear after covering. Clear? Now we start basically deflection. We check the deflection for covering before covering. Clear? And we find out the answer. The answer was 1.83. Now we start deflection for after covering, and basically we calculate the live load. Okay, and now we have to determine the live load deflection. Clear? So we have to calculate basically deflection, and before I start this remaining part, I want to share with you some basic concepts. Okay, I think you already understand, and I hope and I expect that you understand this equation. This is nothing, this is the bending equation, and you see that in bending equation we need a transform moment of inertia, or you can say moment of inertia. As we are looking basically to a composite section, a composite section is basically a combination of 2 or more material. So here we have a concrete section. Clear? And here we have a basically a steel section. Now when basically we are using this bending equation or flexure equation, this is basically the assumption of this bending equation that the material should be homogeneous and a material should be composed of one material, not two or more material. So that's why for a composite section your bending equation do not work unless and unless you convert this material into one common material. Okay, so for that purpose basically we convert either steel to the concrete or either concrete to the steel. So converting steel to the concrete, it is a difficult job. This is a simple approach that convert the concrete into steel. Okay, so converting that steel, okay, we need converting that concrete to the steel, we need basically modular ratio, and modular ratio is nothing that is your modulus elasticity of steel to the modulus elasticity of concrete. Clear? Now you need to calculate the we already know the modulus elasticity of steel. You need to calculate the modulus elasticity of concrete, and what basically we do when we are converting that concrete width or thickness to the same amount of steel, we need this modular ratio. So basically you see here this B by N. This is nothing. This is the equivalent width of the steel to that of concrete. Here basically this term convert that larger width to the smaller width in case of concrete. So here you see in this example, okay, they use the same transform section area concept. They calculate the modulus elasticity of concrete. They calculate the modular ratio, that is 8 time, and you see this is the equivalent width of the steel section in case of concrete if you convert the concrete into steel, and you see that is 10.88 inch. So then they what basically they did, they calculate the centroidal neutral axis, and then you see the whole tabular calculation, and then they basically calculate the transform section. Clear? And then they basically calculate the remaining stresses. So that is the whole procedure behind the transform section. Okay, and now we are come back to our question. Okay, and we start our remaining part. Okay, so where we are basically, before starting the remaining part, I want to share with you that you need to understand deflection. Clear? A deflection is basically the vertical movement of your beam, and remember a deflection is basically in composite section. If we talk about, it is a function of, you can say, movement of inertia, keeping other thing constant. Clear? As you see in this in this formula, if we basically if we consider that these things are constant, so here it is clear that a deflection is a function of moment of inertia. Clear? In lecture number 1, I think so too, I thought about, okay, a little bit to you people. Okay, so here you see, if you increasing your moment of inertia, it will cause decreasing of your deflection, and similarly if you are want to decrease your deflection, you have to increase your moment of inertia. Okay, so basically a moment of, because you already we know that a moment of inertia is a function of the width depth, okay, of the section, and here you see depth of the section play a very vital role. Okay, because there is cubic root. Now in a composite section, basically there we have a very large moment of inertia. Okay, and due to that large amount of moment of inertia, what they basically did, they basically in case of unshored construction, here you can see, in case of unshored construction, we cannot use that large moment of, in the initial stage basically, we cannot use that larger moment of inertia. okay, because the concrete is in fresh stage and we do not use, we have to use that moment of inertia which have a stick section on. Okay, once the composite section begins, composite action begins, sorry, so in that case we are using transform moment of inertia, and that transform moment of inertia is basically what they did, they misleading, or you can say they underestimate the deflection, because that is a very large amount of moment of inertia in case of composite section. So what we did basically, we used the reduced moment of inertia, or okay, we using basically the lower bound moment of inertia, because larger moment of inertia, if we have a larger moment of inertia, so they cause underestimation of the deflection, or they give us a smaller deflection value. So to increase our deflection, because we have to use a conservative approach, so for that purpose basically they also use a reduced area of concrete. Here you see, use of the transform moment of inertia to compute the deflection in composite beam tends to underestimate the actual deflection. This line is very important. This is a research work of these persons. To compensate for this underestimation or lower value of, we have to compute a transform moment of inertia to reduce by one methods. What we basically did, we calculate our transform moment of inertia and reduce it by a 25%. Okay, what value you got for ITR, that is transform moment of inertia, you reduce this value by 25%. Okay, so this means that to overestimate the deflection, or either we can use the lower bound moment of inertia. So what is a lower bound moment of inertia? ILB. In lower bound moment of inertia, basically we convert, we calculate basically the area of the concrete section, right? You see in a composite section, which is at the top of the flange basically. So we calculate the effective concrete area. You can say that concrete area which is effective in and you can say participating in taking the bending. Okay, so we just only calculate that area. And how to calculate that area? We use this equation. AC is that concrete sectional area which is effective, which is taking part in taking movements or bending basically. So that is AC, and AC is calculating by C divided by the stress in transform area, that is your Fy. So we will use this equation. You must memorize this term in mind because we are going to use this one. And the AC which you got, then you have to calculate your ILB, just like you see in the previous example, ILB on the basis of this AC, okay, not on the basis of that actual area of concrete. Clear? That actual area of concrete, we do not use that one, we use this one. Clear? We use this one, this moment of inertia. Clear? So let's come back to the question. Here you see I, and now the target is that to find out this I. So calculate transform moment of inertia and reduce it by 25%. I explained this one. Use the lower bound moment of inertia. Now calculating ILB. To calculate the ILB, you have two approaches. Okay, either you can use this equation. This equation is nothing. This basically locate the centroidal axis or the elastic neutral axis of the section, of the composite section, and you see this AS, that is the gross area of steel, that is the whole depth of summation of Q, basically your C value, that is 735. Okay, and Fy, you all already familiar with these terms. Okay, there is Y2, I already show you in the beginning of this lecture. Summation of Q is clear. Okay, and then you will calculate your ILB, and your ILB is nothing, that is the moment of inertia of the section about its own centroidal axis to the area times this distance. Okay, and similarly the rest of the part. So once you got your location, you have to use this YENA here. So this is a direct approach. Basically Ilb manual uses these two equations. Okay, basically let us, here we see that summation of q in, basically this is this one, and they say, basically they assume basically here that ignoring this, that those formulas, already I use both this formula, and we use the traditional calculation as we did in engineering mechanics for calculating moment of inertia. First of all, to move forward and to calculate ILB, we need this effective area of concrete, which is basically taking part in bending, and their play his role basically in bending strength, sorry. So this is basically 14.1, 14.7. Now you see the actual area of concrete is not this one. The actual area of concrete, you know the width and you know the thickness, and that is the actual area of concrete. But we ignore that area and we only consider this amount of moment of concrete area, and we say that this is the concrete area which is effective, which is basically taking loads, which is basically taking part in bending. Clear? So this is the area, that is 14.7 square inches is only the effective area. So then we need to calculate y2, because already remember the thickness of the section is constant. We just have changed the width. Clear? We calculate the y2 is nothing, that is t minus a over 2. I already do this calculation in question number 6. Clear? We determine y2 location, and then knowing that 18 inches, and we have to fill up this table. Clear? You see components, you see total areas, you see this is the distances basically of each part. Okay, because we have steel, we have concrete. So this y is the, you can say, is the location of the steel centroidal center, okay, to the from the bottom. And similarly for concrete, we will determine that how much its centroidal distance from the bottom of the concrete, clear, from the bottom of the steel plant. Okay, so you see we have a concrete area that is 14.7. we have a W1850, it's gross area. Go to the tables, okay, in chapter number 1 and find out the gross area W1850 section. Okay, and I think so that is an easy task. You just come here, search the table, search the section here, that is your W1210 section, W shape. Okay, remember you have to search in W shape, and we have basically what this is W8 section. Moving upward, you will find your section, that is W18 section, where this is 16, this is 18, and here we have what section? We have 1850 section. Clear? So 46, 1850 section this is, and this C, small c means this is a compact section, and we already check it. And here you see this area 14.7 inches. Okay, this is your gross area here, this one. Okay, so now we got the concrete area already from calculation. We got the steel area. Now this 22.1 is nothing, basically 18 plus this 4.1 inch. Okay, to the centroid of the concrete area to the bottom. This y is nothing, it is this location, and you are ready to know 18 divided by 2, that give you basically this term, 18 divided by 2. Similarly 22 is nothing, it is adding this total uh, thickness or depth to the 4.1 inch. Clear? Then you multiply these two, you got this one. In this term, basically, we have to ignore the concrete moment of inertia about its own central axis. That is BD cubed by 12. We ignore it. And this is simplification, basically, code allow you. And this is the moment of inertia, this section, it is from where it is come from the table, okay? And you see this 50 section comes here, this 50, and here you see that is the moment of inertia. This is the moment of inertia about x-axis. Come down, scroll down, and here you see this is okay. So from table, either from LRFD or either from AIC, you can got that value. D is nothing. Basically, once up to this point, you have to calculate your this value, that is YENA. Remember, this is YENA. Okay. So once you got this one, okay, then you have to determine the total area, and you have to determine the total area and total AY. Divide this AY by this one, okay, you got this one. Basically, this is the central location of this whole composite section. Clear? Now, then we have to calculate this D. So this D is basically nothing, it is the central location y bar minus y1, okay, or you can say D is equal to y minus y bar. Although sign doesn't matter because here we have to check square, so that square basically cancel out your negative positive effect. So here you see the 6.55. So 6.55 is nothing, it is 22.1 minus this value, okay, and here you see 6.55, this is nothing, this is you can see here it is 18 divided by, sorry, this is basically y minus y bar. So this is your y and that is your y bar. So just subtract this value from this, or either this value from this, you got that one. Okay, and then you have to use this parallel axis theorem. This moment of inertia is basically this one is BD cubed by 12. Here we have this one is 0, so we have to only consider basically AD square. So you know AD is 14.7 and B is nothing, this is 6.5. Taking square, you got this one, and similarly for this one. But remember, you have to add this at 100 because you see the formula, and this is a basically parallel axis theorem. So then your lower bound moment of inertia, you just add up these two terms, and here you see 20, 60 and to the power 4. If you use that formula, just plugging the values, you got YENA, and then using the Ilb equation, you see this one. So you have two approaches basically, either to go for your common or your traditional way of calculating your transform moment of inertia, okay, the way you calculate the moment of inertia, okay, use that simple method, or either you can use these equations, which is the AISC LRFD, this equation. Clear? Now we have to moving forward. You see both equations give you same result. There is a good news, okay, there is a good news, and this is pretty cool, because in steel structure, or you can say structure subject, there is also good news, okay. The good news is that one can directly choose this Ilb from table 559. Really, it is a good news because you have to skip all these calculations and you just go to this table and directly choose that one. So let us visit the LRFD manual and find out this value, and try to find out this value directly from table. Remember, in AISC manual we have this table, and LRFD manual we have this one. So here I am using basically LRFD manual. Please such this same lower bound elastic moment of inertia for plastic composite section in this AIC manual. Okay, I am using Ilb. Clear? So you see ILB, this is lower bound moment of inertia. What you have to do here, you must make sure your section, clear, your plastic neutral axis location, and you need this y2 value. So you know that these are our y2 values. Our y2 values is nothing, it is 4.1 inch. Clear? So our required value in between these two values. So we have to make interpolation. Clear? And the section which we have, that is this section, this 800 is nothing, it is the moment of inertia. Now these values basically, what does it mean? This is top flange, and these 2, 3, 4 basically noting or identifying the plastic neutral axis location. If you want to understand this term, you just need to scroll down here, and what you basically need, you just need to click this one, and here you have. Here you see basically what this term means. Clear? You see, this is the location of effective concrete flange force. Yes, this is C. And here you see that what is y2. Okay, so y2 is nothing, it is the location from your top flange to that one. Okay, so this is important. Clear? This is important, and I think so. My assumption in the beginning of the question that I say that y2 is basically the distance from the top flange to the C value or your compression force. Now, the important thing is that TFL basically is the top flange of location. This is point 1. And if you are going in upward direction or either you are going in downward direction, it also matters. Okay. And these C basically you see 6, 7, 8, these are locations, while you see 1, 2, 3, these are the locations above your flange, above your basically your top flange. Clear? So this is important to share with you. Inshallah we do an example in design example on this. Okay, because design example depends upon it. Clear? Now coming back to the part, that is 559 basically. So here we have 559, this one. Okay, we choose our section, we choose our top flange location. Now we have to search our y2 value here, and then our neutral axis location is TFL, that is on the top of the flange. Okay, you see here basically our location of the new this is, we are right now, or P and A basically, P and A is basically on the top of the flange. So scrolling down in between these two values. Okay, so our values is in between here, clear, in these two values. So 2040 and 2140. We have to determine this value for that 4.1 by interpolation. And I think so you all know about interpolation. Interpolation is nothing basically if we draw an inclined line. Clear? If we draw an inclined line, clear, so you can easily got your your value. Okay, so you see, let's say this is your an inclined line, this is the lower portion of that line, because 2040 is lower than 2140. Okay, now what we have to did basically, we have to find out the base and we have to find out the perpendicular. So base is nothing basically, you all know this 2140 value at 4.5 mean that this value is 4.5, okay, from some location, okay, from some point reference. This is this one, and this point is basically 4 inch. If I draw, let's say, this kind of coordinate system, so this point is basically distance 4, and that point is basically the distance 4.5 from the along the from your coordinates. Clear? Now you need to find out this value, but remember you have to mark your required value, that is 4.1. Clear? And 4 versus 4.1 we have to find out this value. Clear? Now assume this value, let's say this is y. Find out this perpendicular. This perpendicular is nothing, this is 2140 minus 2040. Okay, you got your value. Clear? This is 2040. Clear? So this will give you your perpendicular. Now after that, using your similar triangle rule, perpendicular by base and this small perpendicular by the small base. So how we can use, means perpendicular 2140 minus 2040 divided by your base. Your base is nothing, that is 4.5 minus 4 equals to the similar triangle rule, this y divided by this smaller distance, means that y is equal to the smaller distance is 4.1 minus 4. Okay, you can got your y value here, that is 2140 minus 2040 divided by 4.5 minus 4 into this one, that is 4.1 minus 4. Clear? So this will give you y. Now you have to find out this value right at this point basically. So this value is basically nothing, this 20, because you have to reach to this point. So for that purpose you have to add up this y with this one. So that's why our required value of I and B is basically this 2040 plus that y, and you got your y value from here. Clear? So basically once I did this calculation, let me show you. Here you see, remember this is very important point, that A is equals to 1.8 and it is less than TC. This means that plastic neutral axis lies above the top of the flange. Remember, this is very important, like as we did in our rectangular beam analysis or T-beam analysis, sorry. We have to find out A and we compare basically A whether it is more than HF or whether your A is greater than HF. Clear? In T-beam analysis. So if this one exists, this means that your neutral axis lies within the flange and we need rectangular beam analysis. If this one exists, this means that the plastic neutral axis, or you can say your neutral axis, lies within the bevel portion of your, or you can say outside of your flange, and now you need T-beam analysis. So that's why you see here I use the interpolation equation and I got that one 2060, and you see 2060. So this is the procedure how we can calculate a lower bound moment of inertia, and after that did the calculation for the deflection. You see here, they insert all the values. Remember 1.375 divided by 12 to convert the, because this is the load per foot, I think so. So what they did, they convert the load into kip per inch, and this is 40, so that's why they multiply with 12, and because the E dimension in inches, you have to work out in 1 unit. Okay, so whenever you are using this equation, either in your structure mechanics or your structure engineering. Okay, you have to make sure that your units should be uniform. Clear? Now you use your lower bound moment of inertia, you got your deflection. Now you have to check that you have to compare your acting deflection, which is basically existing deflection due to loading, with your limitations, your limiting deflection. For a live load with a uniformly distributed, okay, for a simply supported, the limitation is this one. So that's why we use basically 40 is our span and 360. Once we got the live load deflection as 1.3, and that is more than your acting deflection or your due deflection, you can say. So that's why we are on safe side, and here you see, so live load deflection is satisfactory. And here is my sign, clear, and this winds up. Remember one thing is very important. If you are doing your design, sometimes because it is very important and it is a part of a question paper, they basically say find out such moment of inertia which can support basically a specific deflection, okay, or which limit basically a specific. For example, if you want that your deflection due to any kind of loading should never be greater than this limitation. So what you need, you have to insert this deflection limiting deflection instead of ILB, in place of ILB, and you pull out this ILB here, okay, because you just only crossing terms. Okay, you find out your ILB, go to the table, search the ILB table, okay, because you have a moment of inertia tables, and find out the section, the composite section, which helps you that this is the section which can basically limit your deflection within this limit. Clear? And remember, we also did this the same thing in your beam design as well. If for example a beam section is given and you have to say, you have to want it, or you have to ask that find out such section which can limit this deflection, so then you have to use this procedure. You just need to plug this value, this limiting value 1.33 here, and you just need to pull out this value of I or ILB. For beam this is I, you find out your I, and then going back to your I tables. Remember, you have Z tables and you have I tables. Then you using those I tables, you find out such a section which have more moment of inertia than you have. Okay, so this winds up this major assignment. That is the end of lecture number 9. Basically, remember, in total 9 lectures basically we cover this major assignment. Okay, we covered this question number 6, we covered question number 5, we covered question number 4, okay, we covered question number 3, and we also covered question number 2 and 1. So this ends up this major assignment. If you have any question, any suggestion, any comments, please do your comments, and watch the channel, subscribe the channel, share this channel with others to spread knowledge. Okay, thank you for watching.